Welcome to my channel. Today in this session, let's see Routh stability criterion problem. This is type 2 problem. Already we have discussed the type 1 and type 3 problem. In type 1 problem, for the provided characteristic equation, the Routh table doesn't consist of any zero values. That is said to be as the type 1. And in type 3, for the provided characteristic equation, in the Routh table, one row element is 0. If it is so, it is said to be as the type 3 problem. And in the type 2, we are going to see how it differs from the other two criteria. Our problem is determine the stability of the system whose characteristic equation is given by. This is the characteristic equation, and the characteristic equation is provided by s power 5 plus s power 4 plus 2s cube plus 2s square plus 3s plus 5 is equal to 0. The characteristic equation. Solution for this equation is, as said earlier, we are supposed to form the Rouths table, and Rouths table starting from the higher order. Here the order is provided as S power 5. And how do we say this? The higher order S power 5. In the provided characteristic equation, the number of highest degree polynomial is said to be as the order of the provided characteristics, the equation. Here, the highest polynomial order is nothing but s power 5. And starting from s power 5 and ending to s power 0, I form the root array and I fill the elements of s power 5 by, since it is the ordered term, I fill the first ordered terms as 1, s power 5 term as 1, and 2 s cube term as 2, and the next ordered term is 3 is, I fill this as 3. And next, and the even order terms s power 4, 2s square and 5. In s power 4, I have the term as 1, and 2s square, I have the term as 2, and the last term, the constant term, 5. And from these two row elements, I am supposed to get the s cube term. And starting from the first term, from 1 to 2, I multiply 1 into 2 minus 1 to 2, 1 into 2 divided by 1, which is equal to 0 by 1, which is equal to 0. Anything into 0, the 0 divided by anything which is equal to 0, I have the first element term as 0. And for the next term, 1 into 3 minus 1 into 5 divided by 5, I get the minus term minus 2. Since the s cube term row element, one element is 0, this stability criterion is said to be as the type 2. And further continuing for the s square and s power 1 and s power 0, whatever may be the other values, this tends to be either 0 or towards the infinity. So, the Routh's criterion stability can be checked by two methods. One method is either substituting epsilon for the zero value, or by substituting 1 by z value for the s term in the characteristic equation. This can be provided in the two methods. Why I am substituting these cases? In order to check the stability. How do I check the stability? The first column of the Rouths table must be constant without any sign change. If there is sign change, the system is said to be as the unstable system. Okay. So if there is a zero element, if I proceed to the next order, that is s power 2 or s power 1 or s power 0, and in this you check for s power 0, 0 into 2 which is equal to 0, 0 minus 2 which is the minus of minus, it is plus, 0 plus 2 divided by 0, it tends to infinity. And the next term also will be infinity. And further continuing in such a manner, it tends to infinity, or in the cases of zeros. Okay. So we don't get any stability value, and the system tends to infinity. In order to check the stability, I am going to proceed the characteristic equation with two methods. One by substituting the 0 as epsilon value, or by substituting the s as 1 by z value in the provided characteristic equation. In this, I am going to, first of all, I am going to choose the second case by substituting s as 1 by z in the characteristic equation. Okay, by substituting s as 1 by z, put s is equal to 1 by z in the characteristic equation. This is the characteristic equation which it is given in the problem. Okay. By putting the s is equal to 1 by z, I am substituting this. I get 1 by z power 5 plus 1 by z power 4 plus 2 by z cube. Since 2 by z cube is nothing but I am substituting s as 1 by z. I get 2 divided by z cube plus 2 divided by z square plus 3 by z plus 5, which is equal to 0. And taking the common multiplicand, I get the final characteristic equation as 5z power 5 plus 3z power 4 plus 2z cube plus 2z square plus z plus 1, which is equal to 0. Okay. And once again, with the case of z, I am forming the Rouths table. Starting here also, the higher order term is s power 5. For the provided characteristic equation, the order is 5. And starting from z power 5, I am ending with z power 0. The z power 5, I have the terms 5, 5, odd order term 5, 2, and for z, I am substituting as 1. And for the even order term, 3, 2, and 1 z power 4. And once again, I am constructing the other the terms by cross multiplying the provided terms. For z cube, I am multiplying the 3 into 2 minus 5 into 2, the divided by the same term 3. I get the value was minus 4 divided by 5, and for the next term 3 into 1 minus 5 into 1 minus 3. I get this term as minus 2 by 3. Okay. And for the next case is a square. I am cross multiplying these two values. And cross multiplying, I get 4 by 3 into 3 minus of minus, this is plus 2 into 2 by 3 into 3 divided by minus 4 by 3. I get the value was 2 by 4, and nothing but this is 1 by 2, and the value was 0.5. Similarly, for the next term, cross multiply minus 4 by 3 into 1 minus 3 into, this term is 0, 3 into 0, which I get, divided by minus 3 by 3, is the 4 by 3, which is equal to 1. And for the next term, z power 1 is the cross multiply the z square term and the z cube term. Z square term, this is nothing but 0.5 into minus 2 by 3 minus 4 by 3 divided by 0.5. Okay. And you get the positive value was 2, and next value is 0. I get the 0. Since this term is 0, I am just writing the above term as 1 without any multiplying. If you also multiply this, you get the final answer as 1. Okay. Z power 0 is equal to 1. And our ultimate aim is to check the stability. In this provided Rouths table, you see here from 5 to 3, there is no sign change. For stability check, I need to suppose to check the first column element sign. Okay. And in this 5 to 3, there is no sign change. 3 to minus 4 by 3, there is a sign change from plus to minus. Okay. And there is another sign change, second sign change from minus 4 by 3 to 0.5, and 0.5 to 2, there is no sign change, and from the 2 to 2, there is also a sign change. Okay. And in this, For checking the stability, since there is the two sign change, one from positive to negative and another is from negative to positive, the system is said to be as the unstable system. If there is no sign change, the system is said to be as the stable system. Okay, and now we have proceeded with the stability check with putting S is equal to 1 by Z in the characteristic equation. Okay, you can also substitute the characteristic equation in the in the Rouths array. You can also substitute epsilon value. How do you substitute the epsilon value? Instead of 0, substitute here as epsilon. Okay, and for the next square term, x square term, you cross multiply 2 epsilon into 2 plus 2 into 1 divided by epsilon. Okay, you will get some value, and in this case next term, for the next term, epsilon into 5 minus 0 into 1 divided by epsilon. Okay, you will get some value, substitute in the square term. Okay, and similarly, after substituting s square, finding the s square term value, so there is find the s power 1 term and the s power 0 term, and substitute epsilon is equal to 0 wherever in the equation. You will get some equation here, you get some equation and substitute epsilon equal to 0 wherever you get, and check for the stability. If there is no sign change, the system is said to be as the stable system. If not, the system is an unstable system. So, if one element is 0 in any of the row in the type 2 problem, Routh stability criterion check, you can check by either substituting 0 as epsilon or by putting s is equal to 1 by z. I have proceeded with one form and checked the system and obtained as the system is unstable. If you like this video, like, share and subscribe. Thank you.